We pass to the discussion on materials for the future, and this is led by Hans.
I realize that we are running a little bit out of time, but still I would love to show a few slides before starting a discussion and see how lively you will participate in a discussion. If I may have my presentation. Because in the title of this session there was a remark looking back at the Nano Impact Net, and I would take this opportunity because for me the circle is getting round. The first workshop of Nano Impact Net was also here in Dublin. So I will take a few slides looking back to what happened there, what we did since, and then perhaps trigger a discussion on the new materials. Really the first workshop of Nano Impact Net was also here in Dublin on the minimal and analytical characterization of nanoparticles. We described and discussed the state of the art and identified that at least two analytical methods should be used to characterize the nanoparticles. And I think another important recommendation was that in any paper you publish on nanotoxicology, you should clearly describe the characteristics of your particles and the methods you used. And this, I think, you see nowadays more and more coming in papers, but it's overly clear that this is very important if you want others to understand what you've done and to reproduce your work. The results of this workshop were, after quite some time, laid down in a peer-reviewed paper, showing the results and the impact of such a workshop, I think. But of course, time has not stopped. Discussions went on, for example, on metrics, the size, and how can we relate effects to the characteristics, surface area. There's now a new proposal and a new definition, and if I put it very shortly, it's a generic one, and an important aspect there is that 50% of the size of the particles, the size distribution, needs to be smaller than 100 nanometers. It's a very generic definition, so likely it will require some redefinition upon specific application fields. Another important development since this workshop, I think it started then, is the interaction with the matrix. Corona is a word which you will often hear in the coming days also, I think. And there's a clear need for the identification and subcellular localization of particles, which we did not touch upon too much when we started this discussion. But also some positive things, and I will have a few examples of our own laboratory. I think there's great progress being made now on the detection of particles in media, in products, in tissues. And I think key there, if you relate it to the proposal of a new definition, is that you need to count nanoparticles, and while counting, measure the size, and the chemical identification is also important. Examples of techniques that we use are single particle ICP-MS, and also TEM and SEM are important tools, but they will come back, I think, also in the session later this week. And of course, there are recent developments. The analytical methods continue to develop. So we have made some progress, and I think, well, for the current nanoparticles, but perhaps this is for you to comment on also. We are on the way to develop analytical methods. We are on the way to be able to quantify the exposure either in vitro or human or in ecotox studies. It improved the quality of the literature, but continuous efforts are needed. And now the challenge comes, what are the new materials? In the keynote lecture, I think some new materials were mentioned. If you group them, I group them, but in organic-based nanoparticles, particles with complex composition, and I think an important development will be the functionalization of particles. Quickly, what will happen in my view is a merger of the de-engineered nanoparticle with biology. Of course, biology is built up, designed by nanostructured materials. if you functionalize materials, carbon nanotubes or metal oxides, these fields will merge, and this I think will put high challenges for us on how to characterize and how to measure this. These are some examples which I will skip now. I work in Wageningen. In Wageningen we work at food and healthy life. So trying to encapsulate or bring milk ingredients, for example, in other drinks using mice cells based on various systems. Encapsulation of compounds. And I'm not showing this only to make some advertisement for the university I come from, but also because I think these kind of structures are the materials of the future, encapsulates that survive the stomach conditions, break up in the gut, or even are absorbed and then release their content in the body. Some examples from a food safety and quality perspective. There are also nanoparticles are used and going to be used, for example, in packaging materials to increase the safe storage of food in the supermarket or at home, to increase barrier properties of plastics and their nanoclays, and also a type of compound used. And the idea, of course, is to incorporate barriers to to have a longer route for oxygen or other compounds not to enter the product that is stored within these containers. In preparing this starting for a discussion, I googled new materials, new nanomaterials. I did not find too much, but I did not spend too much time. What I did find was this page from a catalog. Huge number of particles, and what strikes me here is the complexity of the particles. Not only one element, not only a metal oxide, but various combinations of elements into one particle. So likely this is a new type of material which we'll encounter. The functionalization has been mentioned. Some examples here. And then the big question: are we ready for them? Well, I think we have. Starting with the metals and metal oxides, we have some nice fundamentals in the analytical methods, in the toxicity testing approaches. We have some experiences now with interaction with the matrix. But of course, the challenges we encountered 4 years ago and sometimes still have with the standards. Do we have reliable reference materials for all these new materials? The distinction between engineered and natural will go, I think. But then how can you measure them? How can you quantify the exposure? So I think we made great progress as a community in Nano ImpactNet. We have more methods now. But the question is, what are the new materials we will see in the coming 4 years when we work with Q-Nano? And how can we work with them? I gave some examples, so now I would say it's up to you. Which do you think are the new materials we have to start working with? Well, I realize that it's getting late, but I'm surprised to see that no one of you can bring up new materials. So is it really true that we still continue to work with silver, with gold, with titanium oxide? And is that all the future has to bring us? Well, if life would be this easy as the silence of now. Okay. Mr. Chairman, there's no discussion.
Chairman. Well,
yeah? You have?
Oh, but.
Well, I mean, obviously anything connected to silicon, multi-layer, other metals, all these interesting electronic properties that one is seeing emerging. I mean, I think the problem is almost that.
Yes, so obviously the examples include things like silicon, nanoparticles, multi-layers, metals, all of the fascinating things that are going on at those metal interfaces and so forth. I think part of the problem is there are just so many, one doesn't know which ones to look at as being the most promising in a priority list in terms of application.
But do you think that these silicon-based complex particles have new requirements for us? Do we need to develop new tools, new analytical tools, new biological tools to assess the safety?
Well, for sure they exhibit entirely new physical properties. That's the purpose in having them, and new electronic properties. They provide electrons in different ways and in different places, for example, into the environment.
Yeah, that's why we have them.
That's why we have them. And that's going to have kind of very considerable implications in ROS and all of these kind of conventional things. I suppose one could be concerned about the whole question of imaging, right? So it's going to be harder and harder to keep up with finding where these things go.
Yeah.
That's a really big issue. You're going to have to keep following them. And in some ways, imaging tools are really set up around fluorescence at the minute to a fair degree. ICP-MS and these kind of, but finding actually individual particles where they go inside cells and so forth, that'll be a problem. All the wires, I would have thought, must be, right? They must be really of interest to people right now, because the wires are what are essentially nanowires, are communications, again, in electronics. And they're direct analogues of carbon nanotubes. So right now, everyone must be thinking, whoops, are they the same as carbon nanotubes or not, or what, or, you know. Where's the limit? I mean, there's thousands of deeply interesting and exciting problems. I think what we have to do is find a way of prioritizing the ones that are going to be of more immediate have more immediate market access. That's the challenge.
Yeah, so
and then
really
in medicines, I think there it's hardly possible to contain the directions are just so rich.
Yeah.
One is faced with targeting strategies and medicines that involve the surface of the particle. We're barely able to keep up with what's happening there.
So the challenge is to cooperate with people with material sciences, with electronics, with nanomedicine, and then with our view, perhaps mainly on safety, and interaction with biology, and then work together with them.
For sure we've got to do that, but I think the challenge for us is to prioritize.
Yeah.
We have to hope with our limited resources in this community, even if we really work together well, that is if we all don't jump on top of the same particles like the IO2, and if we actually try to segment our work up so that we work as a cooperating community and carve out the space. Even if we did that, we haven't the hope of covering the important areas. It's more a question of trying to decide which ones. You see, these are still in many cases in quite small companies, right? They're fairly new, young R&D companies that themselves have absolutely no clue about the safety issues.
No, and they make potentially very nice materials.
Exactly.
Yeah.
We have 5 minutes left. I don't want to.
There's one other hand coming up.
I think he was waiting.
Oh, sorry. Yes.
Thank you. I hate to break up this interesting private conversation, but
yes.
I would like to bring in one more aspect, and the word has fallen, prioritize. I would also like to add that perhaps the notion of nanomaterial is too constrained, because the nanomaterials are very often in an oxidized atmosphere. And therefore, the surface oxidation can change fundamentally the properties that we're interested in. I'll give you an example. Silver nanoparticles, the surface itself is composed entirely of silver ions. And depending on the oxidative properties of the atmosphere surrounding a nanoparticle, you can oxidize between 1 up to 10 to 15, depending on the conditions. As I mean, I don't need to talk about bactericidal properties of silver ions and all that, but I would like to point out that nanoparticle is perhaps too stringent, too constrained. It's the same idea when you talk about nanomaterials and aerosols. The aerosols that we inhale, of course, comprise not only the nanoparticle, but also the atmosphere, the gas phase that it's interacting with. That's just an idea.
So the suggestion is then that you keep track of how these particles mature or develop or interact, and continue to measure them and see how they interact with biology over time.
Yes, I think that the point is that a nanomaterial is actually too constrained. There's not enough information. You need to define and characterize the nanomaterial properties as a function of the surrounding atmosphere.
Okay, there's one more question. Comment?
Yes. My name is Gert Ruben. I'm from the Joint Research Center. And when I listened to a few of the materials that Kenneth was mentioning, I thought, well, yes, of course, Kenneth is always very right, but I think for this community, obviously not necessarily all nanomaterials are of concern. I think many of the nanomaterials that are being developed are embedded into larger structures and will never, or only in very specific circumstances, lead to exposure. And in these circumstances, there's probably good personal protection equipment available. So I think if you would like to maybe focus the discussion, you might want to change the question: which are the nanomaterials that are of relevance for people like you? Because I'm not a toxicologist myself. And I think there you have to admit that it is still the particles that are the most of most concern to people that have to develop the regulation, for example, in this field.
Yeah. Of course, the risk is also always a combination between danger and exposure. But one comment back would be, of course, all these embedded nanoparticles have a life cycle. So what happens during life cycle, I would add to your comment.
Well, not all. You mention, or you use the word embedded nanoparticles. Many of the nanomaterials are not particulate. So they never exist as a particle. They grow in situ into shapes and forms and structures that are never really a particle. And so there's a lot of new nanomaterials in that area that I hope we never have to worry about.
Michael?
There's another question we could ask. You just showed there are so many materials out there, so it will be, of course, very difficult to test all of them. And in a certain way, if you are a regulatory lab and you have to assess which ones are the ones you should study first, then this is exactly the approach. You look which ones are the big bulk, which ones lead most likely to exposure, and so on. On the other hand, as researchers interested in health, understanding health effects, you might ask not what materials, but what are the properties that interest us, and how can you provide us materials with many different characteristics along that property that interests us, so that we have a nice contrast. For example, keep me size and shape and reactivity and everything the same. I just want to have different functional groups that provide me the same reactivity in certain environments, for example. So maybe we can ask the opposite way around. What can you provide us to study the questions that we have?
Well, you can ask me, of course, but I think that the issue that you raise is reversing the questions and look from the knowledge that toxicologists have and the interaction between particles and biology. That can, of course, be of advantage for product developments or material scientists. I think that's very true. Yeah.
Okay, I think we have to finish the session here. Thanks, Hans, for the work, analyzing. I think that's...
Are there any housekeeping comments? I think we start at 8:30 tomorrow morning. So with that, I thank you for this day and hope to welcome you back tomorrow morning.
Okay, bye.